and we're going to look at the poles and zeros of a system. So we're going to define that right now. So in a transfer function, we usually have, so we'll say you have a plant, some transfer function. We have usually a numerator and a denominator. And usually it's something, let's say as squared plus bs plus c. And on the bottom you have something like alpha s squared plus beta s plus, I'm just going to use gamma because I don't know what the c is in Greek. Alright, so we have some system here, equals. And we are going to use some expressions here. So we're going to look at the poles and zeros of this system. So what are those things? Well, okay, what is a pole? Alright, so a pole is essentially the value of s that makes this system, the transfer function, go to infinity. So value of s that makes transfer function, I'm just going to use TF here, transfer function go to infinity. Okay? So that would pretty much mean the values of s that are the roots of the denominator. Okay? And so we denote a pole as an x, and I'll show you how we plot that in a minute. And then the zeros are essentially the opposite. It is the value of s that makes the transfer function go to 0. So essentially it's going to be the roots of the numerator here. So the value of s that makes this become 0, or the value, so that's the 0. And we denote that as a circle. And then the poles are the values of s that make this expression, the denominator, 0. So let's just do a quick example. So these are the definitions. We're going to take an example. We're going to use g of s, and we're going to say we did our model and we figured out our system, and we end up with this transfer function, s plus 2 in the numerator, and we put it in our standard form, so we had s squared plus 5s. So if this is our starting function, we can find the poles and 0 of it. So first, let's find the zeros first. So the zeros is going to be whatever makes this 0. So s plus 2 equals 0. Relatively easy. We can see that s equals negative 2 is a 0. So this would be our answer for the 0. And then what about our poles? So we take this expression and we want to make it 0. So s squared plus 5s equals 0. We see we could take an s out of here. So we have s times s plus 5 is equal to 0. So here we actually have two poles. So if s is equal to 0, then that is one of the poles. Or if s is equal to negative 5, we have that expression is also equal to 0. So our poles here would be 0 and negative 5, and our zeros here would be negative 2. And what we can do is actually map these on what we call a pole zero plot. Okay, so this is I'm going to write up here, pole zero plot. And essentially all we're doing is mapping s on the real and imaginary axis. Imaginary. That looks weird. But okay, the real and imaginary axis, right? So all we have to do is use these appropriate symbols to map them correctly. So we have a 0 at negative 2. So we go to, we'll say this is, do this. So here's negative 5. 5 here, and about the same here. Okay, so we have negative 2 is one of our zeros, there's no imaginary component, it's all real. So we keep on the real axis and we go to -2 and we put a circle. So that's our 0 at -2. And then for the poles, remember we use an x, we have s equals 0. So again, only real and, well, no imaginary or real components, so just an x, right, at the origin. And then s equals -5, again, only a real component, no imaginary, so we would put an x out here. So this is how we would plot our poles and zeros on the pole zero plane. And we're going to talk about this a lot more later, but we're going to use these values to determine how the system acts. So these values can tell us quite a bit about how it will react to, the system reacts to a step function or to various changes. So we'll look at that later, but right here we just use our system, find these zeros and poles, and then plot them on this type of plot. Valerie has written another one for me, and I guess we're looking at imaginary poles and stability. So we'll do that. Okay, so we have the transfer function again. What we'd like to do is factor it, like we did last time when we had the real poles. But we see when we try to factor this, this does not factor very nicely. So we can't use our traditional method of just factoring and just picking the values easily. We have to do something a little bit slightly more complicated, but still very easy. So, well, first let's do the easier part. Let's find the zeros for this system. So our 0 here would be -1, because that s of -1 makes this numerator 0. So now let's try to find the poles. Alright, so we can't factor this directly, so we have to use the quadratic formula. So for that, we have to find s equal the opposite of b, so -2 plus or minus the square root of b squared minus 4a, which is 1, and c, which is 2. All of that over 2 times a. So there's our setup, and now we just need to solve for this. So we see that if we, well, do one thing at a time, -2 plus or minus something all over 2. So now we have to solve inside the radical. So we have to do 4 minus 8, so that's a -4. And if we solve this out, we'll see that we get a -1 plus or minus. We have a negative under the radical, so we bring out j, and then we just have 2 over 2, so we get 1. So these would be our poles. And here is our 0. So first, let's bring it over to our nicely drawn real and imaginary axis for the pole 0 diagram. And we see that the 0 is at -1, so we put our little 0 here. And then we have our poles at -1 plus or minus j. So we have one here and here. And often these will come in pairs, so they'll be often mirrored across the real axis. And that's the case here. So we have two poles, and they are in, well, this side we call the left half plane. And the right half plane would be this side, so the right side of the imaginary axis. And we see that our two poles are in the left half plane, and we know that they will then be stable.